right. Lastly, researchers from the University of Wisconsin-Madison, including Doctors Xiaopeng Li and Professor of Civil and Environmental Engineering, and Heye Huang, Research Associate, will discuss their project, CAV Platoon Control with Physics-Enhanced Residual Learning. Thank you.
Thank you. Sure, it's fine. Yeah, thanks a lot. Good morning, everyone. So how do we? Oh, yeah, sure. So first of all, I want to say actually we had some communications and thinking that it's better to talk about year one project, but it's going to lead to year two about frictions. That's the title you see on the agenda. So I'm gonna talk about more of the CAV and platooning, and then our colleague Heye is gonna talk about the friction. So this is for platooning. This is a joint work with our colleagues, including Heye and Hangzhou, Penzhang, and Zhao Huiliang, who are our graduate students. So everyone knows what is CAV platooning. It's actually cooperative CAVs driving with shoulder head Vs via V2V communication and automation. This is a piece of video clip that FHWA Turner Fairbank Research Center made, including one of our lab vehicles. That's a red vehicle you see there. It has lots of benefits like increased road capacity, improved traffic safety, and enhancing like energy efficiency. So ideally, what Platoon does is exactly just you have a platoon of vehicles, and the following vehicles are just reproducing the first vehicle's trajectory. Ideally, they want to make these trajectories exactly identical, and this way you could have each vehicle follow another vehicle very closely and without much gap. That's going to generate lots of benefit. But why haven't we been there? So it's because of the control error, actually. There is lots of causes to the control errors, like actuator imperfection and external disturbances, friction, wind, and other things. So if that happens, your actual trajectory is not going to be as ideal as the planned trajectory. You know, there is going to be some deviations, and worst case collision could happen. So how to mitigate that? So a compromise is sure. All right. Sorry. Sure. All right. So the maybe all right. So is the voice okay? All right. Great. So then the compromise is actually you're going to have to increase the platooning spacing, and that's going to lose all these benefits that we mentioned earlier. So how do we address it? And before addressing, let's look at why it happened, actually. A lot of those, platoonings are based on, like this morning's debate, based on rule-based, model-based control. And some of them are even linear. And these are models good for interpretability, but they have issues about the limited control accuracy. So they cannot capture complex nonlinearity or high dimensionalities. Therefore, actually, the actual control is deviated from the planned trajectories. So how do we mitigate this? We propose to augment the physics models with neural networks. So physics model may generate imperfect trajectory, but we can actually augment it by neural network to sort of dampen this kind of deviation and make the trajectory better follow the planned trajectories. And this way we can close the gap. All right, how do we do this? And I'll be really quick here, but I'm just going to introduce the physics-based models. So this is where we start with. Actually, let's look at this diagram. And x-axis are just the time steps. This is the current time, and we have 0, 1, 2, 3, all the way to capital K time points. And we're looking at the number of I vehicles from first all the way to capital I. All right, so now what is the model input to the physics model? It's actually the current state and a future planned state. That's going to be what we want to follow in the following steps. So the current state is actually P for each vehicle I. The current state is included 3 This is location, this is velocity, and this is acceleration. And these are the location, velocity, and accelerations in the future time steps. Basically, you start from here. Each vehicle want to follow its planned trajectories. And the output will be, actually, our control is that instead of like acceleration, we directly go to vehicle RPM because we want to implement it to the physical systems. So this is revolutions per minute is actually directly controlled to the vehicles. All right. And then this physics model is just the mapping from the state to this final control output about RPM. So it has two components. Inside is actually model predictive control, and outside is going to be like a linear mapping. So let's look at the model predictive control part. It actually converts the physics model, converts the states into it's like MPC output is like speed command or something, or acceleration. And that is not directed vehicle control, which is RPM. And we have to convert this speed control to RPM with a linear function. All right, so MPC, I'll be really quick. It's going to be just like look into the vehicle dynamics, and we actually concatenate these vehicle dynamics into matrices anyway. And eventually, we're going to find the best control, which is the speed control functions. That's going to minimize the error between the planned trajectory and the actual trajectory. All right. So then after we get the MPC, we should be able to get to the speed command. But the speed command is not the final input. The final input is RPM. So we're going to use a linear relationship that can be obtained from the data. All right. However, this linear output is not very accurate. That's the very reason that why the control is deviated from the planned trajectories. There is a residual term that is could be affected by turning rate, and also battery status, a lot of other factors, right? You think about all these uncertainties and complex factors involved in this control processes. Right, and even wind and other things, right? So this study, we just focus on like turning state and battery state status to start with. So then next we need to address that residual term. What we do is we're gonna use a residual learning to estimate that difference between the physics model and the actual estimate. So what we do is the input includes the same thing. Besides that, we have this kind of extra factors like turning rate and battery status to incorporate the impacts of these nonlinear factors. And output is residual item. That is actually the difference between the physics model input and the ideal control input of the RPM. All right, so we're going to use a standard multi-layer perception MLP structure to do that, to estimate this U bar, which is the residual items. And after that estimation, so the overall framework is simple. It's just like using physics models to predict the sort of like the first order prediction of the control variables, and then we're going to use a learning term to get the residual, and add them up together. We hope it can get the better control results. All right, so how do we? And this is a model starts from the scratch. How do we make the model work, and how do we do the calibration? So first we calibrate the linear model. This part actually, primarily this linear component, with least square error estimation, linear regression, whatever, to determine its relevant parameters from the offline data. And then we're going to run this CAV platoon and collect real-time data to do some online adjustment, given that battery level changes over time, right? Other conditions changes over time. And to do that, we fix all these linear this linear model and train the residual learning model using backward propagation and with the real-time data. All right, so and how do we get the data? So we actually used I'm going to introduce it later. We used a platform, physics platform, and we used some sensors. Anyway, so let's look at how our system works. like we're gonna use a platform to test the 3 types of models. First is pure physics model. That's the one we used, showed before. Second is pure neural network model, all right, without any physics input. The third is a Pearl, which is what we proposed, physics enhanced residual learning using the physics plus and residues. Let's look at the results. So what is a test platform? We actually started with this small vehicles. You know, it's easy to play with and safe, and also it's quite challenging to control its accuracy. All right. So we have this hardware, and we have 2 scenarios. The first scenario is just to train a single vehicle to follow a planned trajectories, and then second scenario is actually have 3 vehicles following each other to create a platoon. And this is like a video about 3 vehicle platoon control after we apply the results. And they can closely follow each other, and sometimes they may vary the speed and the spacing. You know, like this part they may accelerate. I hope they accelerate. Yeah, accelerate, and then they're gonna try to get to a platoon. All right. So what are the results? Let's look at some of these results, and here I'm gonna show like the speed between the both desired speed and actual speed. Desired speed is planned speed, and actual speed is what the vehicles perform, and over a period of time. All right, this is actually Pearl results. You see, I think for all these different speed steps, it performs very well, and I want you to focus on this high speed range actually. So this is our model's performance, and this is physics model's performance. There is a big gap. This is actually a neural network model, pure neural networks performance. A smaller gap, but still worse than a physics-based model. So why we show that, okay, there is a linear function that does not really capture these complexities. So we actually, use the neural network that can capture some of the complexity, but still not as good as we integrate physics and neural networks. All right, so this is actually a view from the location trajectories. All right, we can zoom into this part, and we see actually for Pearl model, it works pretty well. The planned trajectory overlaps with the actual trajectory. For physics model, there is a big gap. Neural network, there is some gap still, although smaller than physics models. So then that was for the single vehicle test, and then we look into the individual for the CAV platoon control with the 3 vehicles. This is a vehicle 1, and let's look at the speed comparison. We see actually our Pearl model has very good speed profile overall, and the physics model has some large bias, and neural network model actually still has some bias bigger than our Pearl model. All right, these are vehicles 2 and 3, and you can see they still follow the same pattern. So Pearl is the best, and physics model is the worst, and neural network is in between. We actually look into the location tracking these vehicles in a platoon. You see, in physics, because the physics model actually has some cumulative error and doesn't do very well, but this neural network does better, and our model does the best. All right, these are vehicle 2 and 3. They follow the same trend. All right, okay, so if you look them numerically, and I think if you look at the numerically, like the Pearl has the highest accuracy in terms of MSE for this is speed, and this is for location, so Pearl model can reduce the position error by quite a large percentage compared to the physics models, and also some significant improvement from neural networks as well. All right, so we have done a test with the toy vehicles, and we also mentioned we have a fleet of real vehicles we want to test, and also thanks to the MCT 2.0 platform, we hope we can. We have proposed our request to do some their test with their facility. We hope to do some of these experiments. I mean, this first step is just to know how to exactly and accurately control the vehicles. Besides forming platooning, actually, accurate vehicle control can be used for better measure roadway friction. And this is year 2 project. We are still in the process of getting more results, but I want to spend a few minutes to have Heye to present the overall plan about that year 2 project, please.
Thanks, Professor Lee. And now I will be presenting our ongoing CCAT project titled by Roadway Friction Screening and Measurement with Automated Vehicle Telematics and Control. Actually, this project aims to using the data from both regular vehicles and automated vehicles to achieve accurate road friction screening and measurement. We gratefully acknowledge the team from UIUC, like Professor Xiaopeng, Dr. Kell, and Dr. Yiduo, and Dr. Yu Hui. Those people has support our project for the regular vehicle data connecting. So in this project, we forced to connect data from both regular vehicles and automated vehicles under various road conditions. So why we need to connect data from both data sources? And in this figure, we can see the connecting method have different cost and accuracy. So we want to find a balanced way to both achieve cost-free and also achieve high accuracy. So we connect data from the both sources. With this data, what we can do, we want to achieve the peak TRFC value, tire road friction coefficient. This is the basic function of friction coefficient and the slip ratio. So if we want to achieve the max road friction, we need to achieve the peak value. So how can we do that? We know that we have already connected data from regular vehicles and automated vehicles. So as you can see, the pink sampled data are connected from regular vehicles. So if we can collect data from these vehicles, we can fit the slope ratio figure, the curve of this slip ratio. So we can get the like a smooth curve, but we can't find the peak one. So if we can, using the accurate and precise control from autonomous vehicle, we can get the peak values. That's the value that can be calibrated from both regular vehicles and autonomous vehicles. Here is a simple studied case that we connect data, the regular vehicle data from the Xiaopeng County main road. So as we can see in the red fingers, this is a traffic pattern obtained from the traffic count sensors. With this showcase, we can obtain that if we connect the data using the passenger's car just driving around the world, so it can be easier to get more data, and we just need to fit the others from the autonomous vehicle to achieve the peak value. So in conclusion, if we can do this project finally, what we want to expect is that we believe that with this project, we can achieve the accurate road friction measurement, and with accurate road friction measurement, we can need to a much safer transportation system. Okay, thanks for paying attention to that.
Yes. Do we have time for questions? Yeah.
Thank you. I'm Yuji Fuji from Washington Community College. So I guess you're talking about tire friction, but because friction depends on, for example, that interaction between vehicle and road surface. So and it changes based on so many factors, environmental factors, but also even the vehicle, tire pressure too, temperature as well. So how do you account for those changing conditions? And that's my first question. Second question is about platooning. And in a real life situation, there are, again, so many factors, such as a grading, grade. And that's not, just based on your presentation, I'm not seeing that critical environmental conditions. So I guess in the lab, model can be so simple, but in real life can be very, different. So neural net looks very good, but neural net needs to be able to account for actual drive conditions. And how do you do that for real life applications, for real time?
Sure. So, in short, actually, first question. So, friction. We do online estimation. So that's a friction at that moment the vehicle measured is specific to the vehicle to the road condition. So it of course over time it's going to have variations. So for about platooning, it's just like now we have the framework. We only consider 2 factors, but we have 3 dots over there. That means if you add more factors, you just need to measure them and put it into this framework, and it's going to make the model even better. Yes.
Hi, Professor Lee. Thanks for the presentation. And I also have a question about this research. What are the advantages by using MPC with residual learning compared with some pure model-free methods such as reinforcement learning?
Yeah, MPC is actually can solve the exact optimal solution. Reinforcement learning is a heuristic essentially, and also it's for this part is your question is the difference between reinforcement learning and MPC, right? So yeah. And also the reason we use MPC is actually it's going to give some intermediate output like velocity, but we still need some transfer to get to the final direct output actually. So, but we think it's MPC is just fast and exact, and we have actually neural network already following that to capture the part that MPC doesn't capture.
One last question. No? Okay. Well, let's thank Professor Lee and Professor... Oh, you have one?
Hi, Varadrai from University of Minnesota. So I just had a question. So did you try the stop and go behavior for the residual model, like its acceleration and decelerating? But did you try the stop and go where one of the vehicle stops and then starts going again and the vehicle behind also stops?
Yeah, we don't have I'm sorry, can I use this? Sorry. Yeah, just this is we change the speed. It's not exactly from stop to go, but we have speed changes, which is creates traffic oscillations. Yeah, you see with our method it can follow, just react to the stop and go fairly well and reproduce the results. Of course, it's not going to be as ideal as a linear like speed, but constant speed, but still it performs fairly well.
Yeah, another question. So in the video that you showed, what are you using for steering actually? So are you using the same turning rate for the vehicle to steer? Or is there some other algorithm where the vehicle is able to make those turns?
Yeah, we use the default algorithm. They have some line tracking algorithms, but we use that turning rate as input to revise our longitudinal control platooning to make it perform better.
Okay, thank you.
All right, thank you very much, Dr. Lee, Dr. Huang.